Hey everybody! So it turned out problem 73 was the one most people voted for, so it wins, and that's the one I'm going to do. So 73 from chapter 6, here we go. A child of mass of 400 kilograms is in a roller coaster car that travels in a loop of radius 7 meters. At point A, the speed of the car is 10 meters per second. At point B, the speed of the car is 10.5 meters per second. So that's at point B. Okay, so assume the child is not holding on and does not wear a seatbelt. A lot of people had quite some comments to say on their homework. That made me laugh. What is the force of the car seat on the child at point A? So force of the car seat on the child. And then what is the force of the car seat on the child at point B? So point A and point B. And then lastly, it's asking what's the minimum speed required to keep the child in his seat at point A. All right. So once again, here's the diagram that you're doing. It's the one that's below the problem, not above the problem. I apologize. I wish this book would use figure notation to tell which figure to look at. But okay, so I wrote out, drew a diagram right here. I got my radius here, and then this is my point of interest. It's asking me what is the force from the seat on the child at the top there. I got the mass of the child is 40 kilograms, the radius is 7 meters, and the velocity at this point is going to be 10 meters per second. So I'm going to draw a free body diagram here. Again, the child's moving this way with some speed, 10 meters per second to be exact. So I need to draw a free body diagram of what forces are acting here. So obviously there's going to be the weight of the child, mg, that's going to point downward. And then lastly, well, let's see. What's the force from the seat on the child? So this car here is going to be like this. And the force from the seat on the child is going to push the child down that way. And that's essentially the normal force. Or we can call it a normal force. So I'm going to say it points downward, some normal force. I don't know if it's bigger or smaller than mg, but now we're going to calculate it. All right, let's do it. So it's going to be, let's see, F net equals ma. That's always the next step. We're going to go to the second law. And again, just because it's pointing down does not mean we're going to call it negative. We're going to say if it's pointing towards the center of the circle, it's going to be positive. And if it's pointing away from the center of the circle, it's going to be negative. Again, I said that's the best way to do these kind of problems. Forgot that n. All right, so that means then F net's just going to be the normal force plus mg equals the mass times the acceleration. And it's a special type of acceleration. It's centripetal acceleration. And we got an equation for that, but I'll plug it in at the end so I don't have to write as much. So let's see. Now I'm going to isolate Fn by subtracting mg from both sides. That's going to be Fn equals mac minus mg. I'm going to factor out the m. And in factoring out the m, I'm also going to plug in v squared over r for ac. Because my centripetal acceleration, we got an equation for that, v squared over r. So I could take all that, plug it in there. So it's going to be v squared over r minus baby g. And now I just need to plug everything in. So it's going to be the mass is 40 kilograms. The speed is 10 meters per second squared. Radius is 7 minus, I'm going to say 10 for baby g. And that's what my normal force is going to equal. Let's see, it's 100 divided by 7. 100 divided by 7 minus 10 times 40, and that's going to give me 171 about, or about 170. I would say I got about 3 sig, okay. 171 newtons. Highlighted. All right, there we go, 171 newtons. Awesome. Now we're going to go to part B, where it says that we're going to try and find the force at part B here, which is not at the top. It's 30 degrees just below the top there. Okay, here we go. And they also, so everything's the same except, well, once again, we got this is 30 degrees, and they told me the speed is 10.5 meters per second at that point. So we got a speed going this way. All right, I'm going to draw a free body diagram. Once again, there's going to be weight. That's going to point downward. mg. That's the same as last time there. And then there's also going to be the normal force. Let's draw that maybe something like this. So there's going to be a normal force pointing that way. Because it's always pointing perpendicular to a surface, so the child's seats would be pointing like that, so perpendicular to surface would be like that. Okay, so what I want to do here is, well, I'm going to make my axis again like this. Pointing towards the center is going to be positive, pointing away from the center is going to be negative. Well, so the cause of the centripetal acceleration then is going to be both the normal force as well as some component of gravity that's going in this direction. So there's also a component of gravity that's going in that direction that's causing the child to slow down. That's the tangential acceleration here. But then the component here of gravity is causing a part of that centripetal acceleration. And that's what really I'm going to use because I know information about the centripetal acceleration. So what I want to do is find out what that component of gravity is going to be, that y component of gravity. So, all right, it's going to look something like this. This would be mgy. And I know I can use, these are parallel lines, and I got a segment in between there. So that means if this is 30, this also has to be 30 degrees. All right, well, I can find out then mgy. Mgy is just going to be, let's see, if I'm using trigonometry, it's going to be mg cosine of my angle, 30 degrees. All right, now that I got everything, I could just plug into the second law, F net equals ma. My net force in this case is going to be the normal force plus mgy, which is mg cosine theta. So again, they're both pointing in the positive direction, which is towards the center of the circle. So this is going to be equals mass times the centripetal acceleration. Again, I'm going to isolate Fn, so it's going to be Fn equals mac minus mg cosine theta. I got an equation, so I'm going to do two things. I'm going to factor out the mass here for both of these, and then I'm also going to plug in that AC equals v squared over r, and then I'll be able to calculate. So I got Fn equals m v squared over r minus g cosine theta. All right, plugging in now, so I'm going to get Fn equals 40 kilograms multiplied by the speed is 10.5 this time squared, divided by the radius, which is still 7, minus 10 cosine 30. All right, let's calculate that, see what we get. So Fn equals, holding my breath, 10.5 squared divided by 7, and then this minus 10 cosine 30, wrote 11. All right, times 40, and I'm getting 284 about newtons. Got it. Let's see. And it's a little bit bigger than Fn up there. Well, it's going faster. That kind of makes sense. All right. So let's see. So, what minimum speed is required to keep the child in his seat at point A? What minimum speed is required to keep his... okay, so this kind of has to do a lot with... So again, we're at the top here. What minimum speed is required, they're asking us. So there's a bit of a trick to this. Well, kind of a trick, but if you can reason your way through it. Remember when you guys were spinning the ball on a string, right? And at the top, well, you had your free body diagram, and you basically had mg pointing down, and you also had the tension force pointing down. And you realize that as you spun it slower and slower and slower, that tension force got weaker and weaker and weaker until basically, if it was just barely making it over, the tension force was equal to 0. You saw that slack happen in the tension force. Well, that's essentially exactly what's happening. Not essentially, it's exactly what's happening right here, except now it's the normal force that's going to get weaker and weaker and weaker if we go slower and slower and slower. So there is a minimum speed you need, though, in order to get over. So what is that minimum speed? Well, it's when the normal force is equal to 0. So in order to get the minimum speed required, that in that special case scenario, that's when the normal force is equal to 0. That means my free body diagram is just going to be mg, and that's it. That's the only force that's acting there. If you can think about it, this is basically a free fall problem. Don't believe me? Well, watch this. F net equals ma. And my net force is just mg. Again, we're saying positive direction is towards the center of the circle. So it's going to be mg equals ma. And then it's a centripetal acceleration. I can plug in for my centripetal acceleration, it's v squared over r. Ooh, and then also my masses cancel out, hence free fall. My acceleration is g. So this is going to be g equals v squared over r. Now I just need to isolate v. So to isolate v, I'm going to multiply both sides by r and take the square root. So it's going to be square root of rg equals v. So that's going to be the square root of my radius is still 7 meters. G I'm going to approximate to 10. So I basically need to find out what the square root of 70 is. And it's 8.3, we'll say 8.4 meters per second. And there you go. That's the minimum speed required to reach over. All right, so hope that was helpful, and hopefully I'll make another one this weekend. All right, bye.